supposed to drive. Share. That means progress. Try that. Let's try that. Back to where we go. Okay. Sorry about that. Let's try that. So we're talking about files. Now, the reason why I like to lay this out like this is because I'm going to use the term path in this class. A lot of people don't know what the path is. When I say the word path, what I mean is a sequence of directories to get to a file, right? So if I say, what is the path to the file? It's going to give me /user /Eric /this /that all the way to /folder1 /world.txt. That's the path to my file. Okay, it tells the file system where is this thing. Okay, that's answering the question. Okay, now in Windows, directories are called folders as well. We use the term directory in Unix, and so that's the term I'm going to be using, but folder works as well. Here's an example of a path. This is my home directory on Cynet. If you type the command get working directory, get wd, it will tell you where are you on the file system right now. Where are you sitting when you're running this R session? Get wd, open bracket, close bracket, home, S, Cynet, EJ Spence. Yours will look different on your machine. Probably it'll be C:/users/ whatever your name is, or wherever you happen to be sitting at the time. Okay? R has a whole bunch of commands that are available for understanding where your directories are. Checking to see if a directory exists. dir.exists. Temp. Does it exist? No, it doesn't. False. Okay? dir.create does exactly what you would think. Inside the directory you're sitting in, it's going to create this directory called temp. Now you can check. Does it exist? Yes, now it does. All right? Set working directory means change my location, change to where I want to be. So if I set the working directory to temp, and then you do get working directory, the same command is up here, you'll see that I've moved up one or down one, depending on if you're in Australia or not. Does that make sense to everybody? Okay. This is called a relative path right here. I didn't type the entire path, right? The entire path is /home /s /Cynet /EJ Spence. This is the relative path, meaning relative to where I'm sitting right now, create this directory. Okay, relative paths work in Linux. I assume they work in other operating systems that run R, but I don't know that. You'll have to check for me. Certainly, it almost certainly works in a Mac in a terminal, but you'll have to check, okay? Does that make sense to everybody? Yes, we're okay? Okay. Should be fairly straightforward, I think. Now, there are similar commands for managing your files in R. File.exists. Does this exist? Oh, it happens that there's an output.txt file here in this directory. The paths, we talked about this earlier, the path is the full location of where your file is on the file system. But by default, R does not give you the full path. It gives you the relative path, which is a little puzzling. File.path, output.txt, and it tells you, oh, it's output.txt. It's right here. As for the directory, give me the name of the directory where output.txt is sitting. It'll give you the period. Those of you that are familiar with the Linux file system and the Unix file system know that the period stands for right here. That's what that means in Linux. If you're not familiar with that, then that will be a little puzzling to you. I don't know what Windows gives you when you do this. It's a little puzzling to me. I would have expected by default that it would have given you the full path. I want the path. Give me the path. Well, it only gave you the relative path. You have to use this command here, normalize path, to get the full path. That's what I really wanted, right? For output.txt. Okay, there's the directory. Give it the directory name here. Well, where's here? Well, normalize path, home, S, Cynet, EJ Spence, temp. Okay, that's the command you want to get the full path, to get the entire thing on the file system. Okay. Good? Okay. Suppose you want to write to a file. We're going to do a little bit of writing to a file. This is text now. Don't abuse this. We'll talk about this more. Only use this for small files that you need to read. Okay? There is a temptation. I'm going to jump ahead right now. There's a temptation to want to write everything as text. It's easy. It's fast. Boom. There are my commands right there. There's everything you need to write in text. If you're writing a lot of data, don't use text. We'll go over this throughout the class, okay? I know your instinct is to do it. There are better ways, and we'll talk about it, okay? This is just for illustration. If you need to write a little configuration file or something that's very short and you need to be able to read it, sure, use text. That's fine. If you have data that's thousands of lines long, don't use text, okay? So, writing a quick text file, there are a few commands here that'll do it for you. The most basic one is open a file. F is assign the value of file, some file name, and then W means write. I'm going to write to this file. There are a number of things you could put in there. You could put R, which means read, or you could put A, which means append. Okay? This is telling the operating system, what am I going to do with this thing? Right? If it's reading, the operating system will do certain things to the file when it gives you the information. But if you're writing, it does other things. It needs to know the difference, what your plans are for this file. Okay? F is called a file handle, the handle I use to manipulate my file. Right? So I can use write lines, hello, and then there's the handle telling it where I want to put this thing. Write lines again, world, F, and close. Close closes the file. Okay, it flushes the buffer, writes everything to file. The file now exists and it's full. Okay, that's one way to write a file. Another way is with the write command. One shot, boom, open, write, close in one command. Handy. Okay, file name, what I want to write. It'll open it and close it for you. You don't have to close it. Okay. Cat, we've seen cat before. Normally, it'll just write to the command line or to the screen, but you can tell it instead, no, I want you to write to this file. Write this to this file. You can append. If you don't append, it'll overwrite whatever was there before. Same with write. You have to tell it to append, or else it'll wipe out whatever was there. Okay? Similar to this, right? If output.txt existed and you wrote write instead of append, it would overwrite whatever was there. You need to tell it, keep what's there, stick it at the end, whatever it is I'm adding. Okay? The catch with cat, and we've seen this before when we've used cat, is that it doesn't stick a new line on the end of your output automatically, right? By default, it just writes the text and then your prompt comes after it because there was no new line. So you need to add your new line if you want it to look nice, okay? There are other ways to write stuff that are more complex. Write CV, write table. We're not going to cover those today. Okay, generally speaking, you don't want to be writing this stuff in text. Okay, there are better ways to do it, and we're going to go over them today. Again, this is just for a quick configuration file, a quick note, whatever. Okay. Questions so far? Okay. Come on. No? Sync. Okay, we've seen sync before. Okay, another way to write to file. We've used it in the past for saving commands, right? You do sync output.txt, output2.txt, and it will start dumping things to the file instead of dumping them to the screen, right? We've seen this before. Print hello, print do a bunch of stuff, print this. You'll notice that nothing's coming to the command line, right? Nothing's printing to the screen. The output's not going to the screen. Turn it off with sync null or sync just open bracket, close bracket. And then once again, stuff starts coming to the screen. And you can see what was put in the file by either cat or less or whatever your favorite command is for looking at the contents of a text file. And here they are. One, hello. That goes with this one. Do a bunch of stuffs up here. 2 plus 5 is indeed 7. Okay. Now remember, and this is unfortunate, I think, that sync does not give you the command that was written, right? It only gives you the output. So if you wanted to know what this stuff actually was, you'd have to say, here is the value of, and then put it, output it using cat or paste or whatever your favorite command is, right? Recall also that you can use the split equals true argument in sync so that it will print to the screen and to the file. So you can see both while you're doing stuff. If you want to do some work and you want to remember your commands, so you save them to the file, but you want to see the output as well, which is handy, obviously, you can use split equals true in your sync up here. So sync output 2, comma, split equals true. Okay. Good? This should all be review, I think. Okay. Oh, this one? There we go. Read lines. Okay, so you've dumped a few lines to file. Now we want to read them. Very similar to before. There are a number of ways to do it. F is your file. Read lines. Read lines, if you don't give it anything else, if you just give it the file handle, it'll read the entire file in one shot, which is often very handy if that's what you're after. Okay. If you don't want to read the file in one shot, you have to specify n equals 1, 2, 3. How many lines do you want, right? By default, it's the entire file. So if you do this read lines F, it'll give you an array, one with 3 elements in this case, 1 for each line. Hello, do a bunch of stuff, and 7. This is from the previous slide, right? So an array with 3 elements. Okay. Interestingly, I can do this twice. Most operating systems won't, not operating systems, programming languages won't let you do this. Normally, you open a file, you read through it, and you're done. That's it. Okay, if you want to read it again, you have to close it, open it again to go back to the top. R will let you go right back to the top, and you can see that here. F, I read the entire file with read lines, and then I read it again. A is read lines F, structure of A. Character array of 3 elements. Hello, do a bunch of stuff, 7. Okay, so you can keep reusing your handle if you want to in R. Normally, like I said, it gets to the end of file at the bottom and it stops, and that's as far as you get to go. R says no, they probably want to go back to the top, so it jumps back to the top and you can keep going. Okay, again, use close to close your file. And again, read CSV, read delimiter, read table. There are a bunch of commands out there you can use. Read CSV, you've probably used this for your second assignment. Or read table is another one that some people used. Okay, they're handy if you've got a big text file of CSV data, but that's not the best way to store your data, and we're going to talk about that. Okay, it is very common, but it's fairly inefficient. One more thing about files. Wildcards. Those of you that are familiar with Unix and know how to get around in Unix are familiar with the wildcard star. It's used for filling stuff in using the shell. If you don't know what this is, don't worry about it. I'm just throwing it up here for people who are familiar with it. Use the glob_rx, glob regular expression command to grab blocks of files like this. Okay. Pattern equals glob_rx.text directory, and it gives you, in this case, 3 text files. If you know what this is, great. If you don't sweat it. Okay, not that important. Siki. Glob2? Oh. May depend on the version. Yeah, I thought this was correct, but it could be wrong. It's been a while since I tested it. Okay, so possibly glob2rx. Regular expression, that stands for, which is the Unix term for what this thing is. Questions? Okay. Now, let's talk about doing things efficiently. As you've probably noticed, we're not just teaching you R, but we're forcing you to do things the way we want you to in your homework assignments, which means using functions and using Git. And these are the reason we do this is because these are good programming practices. This will make you a better programmer if you do things this way. We don't cut and paste huge blocks of code. We use functions, we use loops, we reuse things as much as we can. So another thing that we see people do and we don't want you to do because it's not good is to do a lot of IOPS, input and output operations, okay? You want to minimize these as much as you can. And the reason is because it's slow. It is really, really slow, okay? The disk, the spinning disk is by far the slowest part of your machine, okay? If you're on your laptop, working on your desktop, you probably don't notice, okay? It's pretty fast. If you come to SciNet and start doing lots and lots of IOPS, we're gonna come hunt you down because it will bring the system to its knees, and it has. Okay, and that has to do with the fact that the system is designed for big files and not very many of them, not hundreds or tens of thousands of small files, which is what some people tend to do. Again, not to be cruel, but it's always the biologists. The geneticists in particular love their tiny text files. Okay, they do. And seriously, you will kill SciNet. It will bring the system down. You can't do that. So here's an example of how not to do things. Okay, we've got this string, hello world. For I in string split. String split's just going to slice this string up into characters. Boom, 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 boom. Okay, we're going to write one character at a time. Cat, file, I, file F. Not only are we going to write one character at a time, we're going to open the file and then close it, and open it and close it, and open it and close it, and open it and close it. Okay? Then we add a carriage return at the end, a new line, because we need to with cat. There should be an append equals true at the end of this. This is the correct way to do it. You don't need an append equals true on this one, right? Here's your string. Open the file for writing. Drop the entire string in one shot. Close the file. You're done. That's the right way. One IOP. And this has 12 or 11 or whatever it is. Okay? You want to minimize them as much as you can, especially when you're using text files. Do what you can. Load things into memory once, reuse data. Don't write until you have to. Write as much as you can in one shot. And use RAM disk if you can. If you know what that means, great. Again, if you don't know what RAM disk is, don't sweat it. We're not going to worry about it. Okay? It's like fast memory. Good? I've seen people do this or things like it. They'll be inside a loop, and they open the file at the beginning of the loop, and they close the file at the end of the loop, and they're writing as they go. Don't do that, okay? You can open it outside the loop, right? You can close it at the end of after the loop's done, okay? Keep your file handle open. Okay. Now we're going to talk about text versus not text. This is a big deal. Makes people nervous, and I understand that. I'll admit it, when I was a grad student and a young postdoc, I used text all the time because I didn't go to a class like this, because they didn't exist in my day. And the nice thing is that it's beautiful, right? It's text. I can read it. I can just pull it up in a text editor. I can pull it up on my screen, no problem. I can read it. That's fine. But it's not very efficient. There's a lot of work going on underneath that you don't see. Okay, this is in contrast to binary. Okay, binary is the alternative to text. There are others, we're not going to go into them. For our purposes, let's pretend there are only two types of files, text and binary. Binary means we're going to dump the data to the file exactly the way the machine sees it when it's in memory. I'm going to take what's in memory, just drop it to the file. Boom. Okay, means something to the machine. Doesn't mean anything to me. I can't read that, right? You pull that up, you'll see all kinds of gobbledygook, right? No good to me. Okay, but it's fast and it's efficient for space and for time. Okay, there are lots of binary formats out there, NetCDF and HDF5 in particular. We're going to talk about NetCDF today. Okay, let's talk about text a little bit more, just so you have some text theory behind you. Okay, ASCII was your original text. All right, 7 bits for a character gives us 128 possible characters. Here are some of them. Okay, only 95 are printable. The rest are things like tabs and new lines and what have you. Okay, spaces. Okay, we use 8 bits to store it. It's not very efficient, okay, especially for numbers, 0 through 9, right? Okay. When ASCII represents floating point numbers, it's turning each number into a character, right? So each character in your number gets a whole byte, as opposed to a float taking 4 bytes of information. It's going to take, for example, 18, depending on if it's double or single precision here. Okay, it's inefficient. Yes, you can read it, but it's inefficient. And it's slow, because every time you read that thing, it has to go to the file, which is stored in binary, whether you want it or not. It's stored in binary because that's what the machine uses. Converts it back to text so it can put it on your screen. Same thing when you're reading it into the machine, right? It's in binary format, but it's in binary format in text. So when I'm reading in my data to do my calculation, it has to come from binary, get converted to text, and then converted to the form that the machine actually wants to use. Slow. Slow, slow, slow. Okay? We don't want to do this if we're using gobs and gobs of numbers. There are a number of text encodings out there. Okay, ASCII's the one that, for those of us that only speak English uses 7-bit encoding. Latin 1 has 8-bit encoding. Most Western European languages are covered with that. UTF-8 and Unicode cover just about any character you could possibly use. Okay, Japanese and Chinese and everything else are in Korean. They're all in there. Arabic, I would imagine, as well. R can deal with this. Okay, if you want to write your code to print out things in a different language, that's totally fine. You want to use the encoding function, okay, which allows you to set which of these encodings you're using. Okay, by default, it's just going to do ASCII because it's going to assume you're using English. But if you want to use Latin 1 to add some other characters, or you're going to use a different language altogether that's not based on Western European character sets, then you're going to use UTF-8 or Unicode. Okay, you can use the ICOM function will convert between encodings. Okay, I'll show you an example of this on the next slide. The Unicode escape character is the \U. If you see a \U in a text document, it means that it is a Unicode character. So you're probably not going to be able to read it unless you've memorized your Unicode. And given that there are 110,000 of them, good luck. So you can, for example, X is FA\XE7ILE. And if you print that out, that's what you get, which is not very enlightening. But if you change the encoding, so originally the encoding is unknown, which means ASCII. You change it to Latin 1, then this becomes facile. Okay, this symbol \XE7 is the Latin 1 characterization of the that symbol. I can't remember what it's called. It's been too long since I took my French. Facile. Okay. You know what it's called? I don't remember. CD. Okay. CD. ICOM is the conversion between one encoding and another. So I could have used that one up here, right? ICOM X, go from Latin 1 to UTF-8 and assign it to XX here. Okay. If I look at the encoding of XX, I see, yes, indeed, it is UTF-8. Okay. Again, UTF-8 is bigger than Latin 1. Latin 1's included in UTF-8. So if I print it at XX, I'll see I get facile back. All right. And then, as I said before, \U is a Unicode symbol. I must have skipped a step here. This may not work without assigning the encoding. But this is the symbol for mu, and this is the symbol for, I don't know what that is. I pulled it out of random Unicode characters. I don't know what this is, but there's a LaTeX symbol for it, so I could print it. Anyway, so for those of you that are interested in exploring this, this is how you go about using different encodings for your text in R. Good? This is not really related to today's class, but since we're dealing with text, I thought I'd throw it in. Questions? Yeah, because it's a 7-bit, but not that much faster. I mean, you're not going to notice compared to anything of importance, right? Mm-hmm. That's interesting. How big was the file? A couple of gig text file. Bad. Ricardo knows better. All right, let's talk about binary. This is where we're going. You're going to take your multi-gig text files and put them into binary. And this is why. Okay, the numbers in binary, as I said before, you're just taking your block of memory, you're dropping it to file. Okay, straight up. It's fast and it's space efficient. Okay, if we're on the SciNet file system, which is as fast as you're going to get, okay, ASCII takes 173 seconds to write 128 million doubles. Okay, binary takes 6. RAM disk is like your memory in your computer. Okay, almost the same speed. Again, it'll be even faster because it's fast. It's not spinning disk. This is your RAM. Okay, this should be pretty convincing in terms of speed, right? There's no contest. You can't read it. We know that, but would you? If I had 128 million doubles, I assure you I'm not reading that file. The only reason I might look at it is to look for NAs floating around in there, because my code would sometimes do that because it was not behaving itself properly. But otherwise, no, you're not going to look at this thing, right? Now, it might be tempting to just take your huge block of memory and just drop it to file. That's called raw binary data, okay? We're just going whole hog, just dropping it, okay? And that's fast and efficient, but there are some problems with that. The problem is that you don't know what you've got, right? When you go to read that thing, you better know what it was, because there's no way you're going to be able to figure it out after the fact, right? It's just raw numbers. There's nothing describing this thing. You've got nothing, okay? If I drop a 2D array of 100 by 100 floats, okay, I've got 40,000 bytes there, right? But if I hand this to someone else, here's my 40,000 byte file. What is it? It could be anything, right? It could be a 2D array, 100 by 100, or it could be a 1D of 10,000, or it could be a string of 40,000 characters, or whatever, right? It could be anything. So we discourage people from using raw binary. You can do it. I'm not going to show you how. You can do it. Just drop it. Okay? Don't. You need metadata. Data about the data. Data describing what is this thing, so that when I hand it to the grad student after I graduate, the poor soul is not totally lost, emailing you every day, trying to figure out what this data is. Okay? There are many, many binary formats out there. We don't suggest you create one yourself. You'll hear us say this a lot at SciNet. Don't code as little as you have to, right? Most of the things you need to do have already been done. So use the tools that have already been developed, right? When it comes to binary formats, there are tons and tons out there. It's easy to mess this up. It's really hard to de-engineer a binary format after the fact. So use one that exists, all right? It saves you potential bugs and the burden of documentation, right? Here are several examples. R data, okay? It's an R specific format. We've used it already, or you may have used it already if you used save, the save command in R. By default, uses R data as its format, okay? Can't be read by other languages though, it's R specific, okay? Fine if you're using R. RDS, another R specific languages. It'll only store a single R object though, however. Okay, NCdF. This is the one we're going to talk about today. It's built on top of HDF5. It's great if you're using lots of arrays, array-oriented data. Okay, if you have gobs and gobs of tables of data, this is for you. Okay, contains not only the data, but descriptions of everything that's in there. You can pack all the metadata you want into this file, so that when you graduate and hand it off to that grad student, you can just tell them, read the file. It's all there. Okay? And the reason is because 6 months from now, you're not going to remember how you created that data. I guarantee you. Right? You're going to be sitting there. When I was close to graduating, I had so much data floating around in my working directory, and I couldn't tell you where half of it came from. Because it was, I don't know. I have a sense based on the file name, what I used to make it, but I don't know the details. So I can't trust it. I don't know what it was, where it came from, how it was made. Okay. NetCDF5 also, or not NetCDF4, not 5. HDF5 also can be read by anything. Okay, if you're on a Mac, you're on Windows, you're using C++, you're using Fortran, you're using R, you're using Python, they can all read it. Okay, they all accept the standard. So if you hand it off to someone who doesn't like R, they want to use Python instead, boom, not a problem, they can read it. C++ also can read it. Fortran, everything can read these formats. Okay, so you're not stuck. Works on Linux, Windows, Macs, everything. That's why we're going to go over it. I'll show you how to use it. R data, let's go over the few at the beginning first though. The simplest and fastest, right? If you're just wanting to do something quick, use the save function and the load function. You've seen these before. I mentioned them in the first lecture, I think. Okay, got a bunch of variables. Save, variable 1, variable 2, whatever, whatever, whatever. File equals my data.rdata. Boom, you're done. Saved it for you. Exit. Come back, load my data, our data, and boom, it's there. You didn't have to do anything. It's automatically loaded. There it is. Okay. If you're working and it's the end of the day, you just want to save it and go home, save it and go home. That's fine. Okay. This is not good for long-term storage of production code, though, production results, but it's good for quick. This is also how the image of your R session is saved, right? Or right when you close your R session, it says, do you want to save the image, right? It saves it as a .r data file. Either you specify it or it will specify it for you. Okay. Okay. How much data are you getting? How are you collecting it? How are you collecting it? Are you typing it in by hand? Or is it coming from somewhere else? If it's not massive, maybe Excel is okay. But if it's coming in automatically, then maybe you can just save it as a binary file directly and use it later. I'll show you how to use NetCDF with R in a minute. I just want to go through the binary formats that are available. So I'm not sure that really answers your question, but again, it's very much a scale issue, right? It's just that we see so many files on SciNet that are 10 lines long, and I've got 10,000 of them. Instead of putting them all together, and they're all the same data related to the same problem, and then organizing them in a sensible way in a single file that uses way less. No, text files, all text files. Anyway, we can talk about it. Again, it's a very case-by-case situation, right? RDS files. Okay, I mentioned these earlier. These are a variation on, well, it's not a variation. It's different than our data file format, but it's similar. The differences are only a single object can be saved with an an RDS file, excuse me. Okay, and when it's loaded, it's not loaded like the RData file was, where the variables just appear and pop into your environment, but rather you assign it to something here. So if I have A and I save RDS A to some file, then when I want to read it, B is assigned the value of read RDS. Okay, and you assign it directly as opposed to things popping into the environment. This is a little handier if you just want to save one thing and quickly assign it to something. I really don't like this sort of situation where I load something and goodness knows what just pops into the environment and I don't remember where it came from or what the history of it is. That's not really the way I like to do things. This to me is much more preferable, just because, okay, I'm grabbing something very specific and I'm assigning it to something specific, and I don't have mystery variables floating around that I forgot that I made before my first coffee yesterday, right? Anyway, here's how we use an RDS file. Questions? Okay. Let's talk about NetCDF. NetCDF files, now this is going to be complicated. I'm going to say it right now, okay? Because you're saving your metadata, this is going to look clunky compared to the last two slides, especially. Last two slides, boom, you were done. 1 line, 2 lines, and off you go. Here, it's going to be a lot more involved. But you have to remember that what you're doing here is not just saving your data. You're saving all the information you need to recreate this data. You're saving all the information that describes where it came from, why you made it, how you made it, where you made it. So there's a lot more infrastructure here. So it's a little more involved. There are 3 sections to a NetCDF file. Like I said, NetCDF lends itself to arrays. So the first thing is dimensions. You're going to describe dimensions that describe the axes of your data. Okay, it has a name and it has a length. Then you're going to describe variables. These are your multi-dimensional arrays, usually 2D, but they can be higher D if you want. It doesn't matter how many Ds, really. Okay. And then attributes. This is your metadata. You could have metadata for global, the whole file, or metadata just for specific variables if you want to. Things like units, for example. What are the units of this thing? Okay. The original libraries for NetCDF were in the R NetCDF library and NCdump. We don't use those anymore, okay? You'll see them, don't use them. Use NCdF4. NetCDF4, the latest installment, is built on HDF5, which means that it's very versatile, and this is where the ability to read it anywhere comes from. So we're going to use NetCDF4. So we use the NCdF4 library. Okay. If you're on a machine that has a terminal, you can use NCdump to look at the contents of an existing NetCDF file. You have to have NetCDF installed on your machine, though, so this just won't work out of box unless your machine has NetCDF4 installed, which means it also has HDF5 installed. Okay, so you need, I haven't decided yet if we're going to work this into the last homework assignment or not, because it involves installing stuff, which means headaches for me. So we'll see. NCdump-H means in human readable format, give me the contents of this. Give me a summary. Here's an example. It's going to say, okay, here are this file is called test. NC is your standard NetCDF file name extension. Here's test dimensions. Okay, we've got 2 dimensions, x and y. We've got some variables. These are the 2 axes. Okay, they have units of meters. Now we've got some variable called a, which has dimensions of y by x, and it is unitless. And then I've created some global attributes, my awesome data, the institution is Synapse. Okay, here's an example of what it looks like. Quick summary of what's going on in my file. This is how you write that file. You'll notice a lot more lines than compared to the last one, right off the bat, right? Here's a script that creates that file you just saw. First, we load our NCdF4 library. Okay, here's our variables. First, I create 2 dimensions, x as 10, y as 5. Here's x and y. Okay, you've seen this before. Here's a matrix. Okay, I'm just doing 1 through 50. Okay, it's just a 5 by 10 matrix. Okay, then I create my dimensions. Okay, x and y. I use the NCdump function. Okay, I'm going to call this x, and I'm going to give it units meters. It's going to be a double, and I'm getting rid of the long name because that's an extra feature that I don't want to use. Same with y, except that should be a y. I have to cut and paste more carefully. Then I create my variable, NCvardef. I'm defining a variable. I'm going to call it a. It's going to be unitless, and it's going to have these dimensions, x dimension by y dimension. I'm not sure why NCdump reversed them, because this is correct. Then I create my file, NCCreate. Here's my handle. I'm going to give it the variable definition. You can put a whole list of them in here when you create your variable. Boom, 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 boom. All the matrices I want to save, not just one, all of them. Put the variable in, meaning the actual data, into this file with that, into that variable's definition, and there's the data. We've defined it over here. And then I'm going to put some attributes, NCatput. Okay, 0 means global. I'm going to make it apply to the whole thing, and the title is my awesome data, institution, sign it, and close. You can do it in a terminal. I wrote a script for it, but you can do it in a terminal. It works either way. This is more of the same. Questions? This is just describing the functions, okay? Putting the variable a into a.def. Okay, I know it looks like work, because it is work. But once you get it done, you're good to go. Questions? If without the -h, it will print the data itself. No, it'll print it in human readable format. Whether you can grab specific entries, I'm not sure. The other nice thing about the NetCDF file that I didn't mention, especially, and this happens to a lot of people actually, you'll have some humongous file, multiple gigs, but I only want that little bit over there in the corner. I don't want the whole thing. When you open your NetCDF file, you can reach into the file and just grab the variable you want and pull it into memory. You don't have to pull the whole thing, which is helpful if you don't have enough memory on your machine to handle the entire file. We'll see that we'll see how that's done in a second. Do you have a question? It just I think because it wants a double. This may not be necessary. And that's a mistake. That should be a Y, of course. Okay. Talk about the metadata now. Okay, I'm going to harp on this because this is important, very important. Okay. The reason you want to do this is because now all of your metadata is baked into the file, right? It's in there. It's in binary. You can't just read it, but the metadata is now there. So that 6 months from now, again, you're going to be able to pull up your file and say, where did I make this? When did I make this? What program did I use to make it? What version of the program did I use to make it? What was the name of the code? Where, what operating system was it created on? This is the important one for me. Include the values of key variables that we use to create the data. If I've got some function that has 5 optional variables with default values most of the time, but sometimes I'm tweaking them, those are the things that I never remembered, right? I'm making some fit to some data and I'm tweaking values of my parameters that I feed into my function and I can't remember what values I used. So I have to do it over because I don't know what it was. Put the key values of those variables into your metadata, okay? Anything that will help you understand the what, where, why, and how. Where did this stuff come from? How did I make it? So I don't have to make it again. The important thing is trust, right? Do I trust this stuff? The reason I trust it is because I know exactly how I made it, where I made it, why I made it, what parameters I used to make it, and so on and so forth. Okay, put it all in there. Your name. Be proud of your data. Don't be afraid. Okay, everything should be in there. If you're not sure, put it in. Put in a knock-knock joke. I actually did that once. And the postdoc ahead of me when I was a grad student would drop them into the comments of our code. And so it's fun to debug his code because you never know when you're going to get a knock-knock joke. Seriously, why not? Doesn't take that much space. And everything, seriously, stick it all in there, all right? You can't have too much metadata. I knew people that would take their entire script and put it in the NCDF file. It wasn't long. It was only like 100 lines long. So you just cat it and dump the entire thing right in there. If it's that small, why not, right? And then I can really check what I did use to make this thing. If you have 10,000 lines of code, don't do that. But if it's a tiny little thing, sure, why not, right? Put it all in there. It's not that big, right? Compared to the data itself, it's not that big. It saves you time, okay? It's really going to save you time. This is how you read it. Once you've created your file, got your NetCDF file, open. Print will do essentially what NCdump did from the command line. It's just going to print a summary of what this file has in it. Okay, so we've got A of dimensions X and Y. It's unitless. We've got X and Y, units meters, got some attributes. Okay, it's in NetCDF format 4. Okay, if I want to reach into my file and just grab one particular piece of it, I do ncvar get. That's the file handle from the previous slide. There's the name of the file, which we took from here. X, this guy. Okay. Print it. Boom, there it is. We saw it from before. It's just 1 through 10. Okay, I can reach it and grab A. This looks trivial here, but when, like for the climate, people use these all the time, right? And they have huge data, terabyte files. They don't want to read in the whole thing. They just reach in and grab the piece they want. Okay. NC@get, attribute get the attributes. Okay. Institution. It's going to return a named list, actually. One is, has the attribute. Does this thing in there? Yes, that thing is in there. Has attribute. I don't know why there are 2 S's. Value. What is it? Sign it. Okay. It's not hard. At least in R, it's not hard. Questions? Time. Oh, look at that. It's like I know what I'm. All right. Final tips. IOPS. Okay. Don't create millions and millions of files. Okay. Slows, especially, I didn't mention this, it slows down your directories. You have more than 10,000 files in your directory, you can't list them anymore, right? You do ls and your file system just sits there and waits and thinks and thinks and thinks as it tries to figure out what you've done. Okay, don't do that. Letters and numbers and underscores and periods and file names. Don't put spaces in, okay? This save us Unix people from having trouble, because a lot of what we do doesn't work with spaces very well. Try to minimize your IOPS, okay? Reading and writing when you have to do it, and we do all have to do it. Write in big chunks, read in big chunks. Don't jump to little pieces. Don't do little pieces at a time. Don't open and close files over and over and over again, okay? If your data is not text, don't save it as text. Okay, sort of the moral of today's class. If it's a number, save it as binary. Okay, as a general rule. Again, there are exceptions, but especially if it gets big enough that you're not actually going to read it yourself. It's that big, make a NetCDF file for it. And again, choose a binary format that's portable. NetCDF is the one I recommend. HDF5 is better depending on, in certain contexts, it's better. If you have arrays, NetCDF is better. HDF5 is better for things like graphs and things that are not arrays, essentially. Questions? Yes, sir. What are you searching for? Of words? Or it's a text? It's a text file already? Or it is text? Or is it, what is your data? The binary is going to be faster, absolutely. There's no question. Binary is always fast. The pipe. Mm-hmm. Right. Which expression? Sorry. Sed. I don't know if sed works in R. Sed will work on the command line, certainly. Same with grep, yes. Okay, well, you'd have to. Yes. See me after class. Sure, answer is yes. I don't know how to do it in R. We could do it in Python, because you can directly reach in and grab the standard out and grab it and pull it right into Python, and then use that to dump to NetCDF. Not sure how you would. I don't know of a utility that will create NetCDF files from the command line, because that would be the obvious thing. Just pipe it to the command line, right? Can you pipe to a NetCDF file? No, I don't think so. There's no utility that would do that. Capabilities. So the short answer is yes-ish. Well, the best suggestion I had was to have Python grab the standard out and then use Python to create the NetCDF file, but I'm not sure if there's a better way. Or just do everything inside the Python. You can use sed and grep, certainly grep. I'm not sure about sed, but most of that functionality already exists in there as well. So Other questions? Good? All right, dismissed. What's that? On Sinet or on dev shmem? So there's a when you're on a node, you just do make directory. You don't even have to do that. Dev shmem Ricardo's stuff. And then just use it. And then at the end, you're done. Move dev shmem Ricardo's stuff star somewhere on Scratch. You got to get it off right when you're done, because when you go, it disappears. So at the end of your script, move the stuff wherever you need it.
This is like where the RAM is.
That's where it's mounted. So if you have enough memory, this comes from the memory. So you only have 16 gigs. After operating system, say 14 and a half or whatever, if you whatever's left over after you're running your used memory, once you've loaded up your data and everything, whatever's left over is available here. Up to 10 gigs or something, 11 gigs for dev.
11, I think, yeah.
There's some maximum, but it's a fair amount. So yeah, you can do all your IO stuff here if you need to do a lot of this, because it's super fast, it's local. And then when you're done, just get it off there.
But you still really get the gains when you're binary on RAM.
Oh yeah, absolutely, yeah. If there's any temporary IO, do it here. Obviously not permanent, or even permanent, as long as if you're just dropping little bits to the end of your file as you're going along through your job, do it there because it's faster and it's local. And then when you're done, move it off. Right. Totally faster.
Just so you know, the standard data generation instruments.
Yeah.